All right, so tonight we're going to talk about church encoding. Church encoding is probably one of the most exciting topics for me in the course because it illustrates something that I think is particularly cool, which is that you can program if you just have the Lambda calculus. So if you have nothing else but just the ability to create functions out of lambdas, variable references, and then apply functions. If you just have those three things, then you can build an entire programming language. And that is in fact what we're going to do in assignment A4. So church encoding is a process of encoding all of the values in our programming language. So things like numbers, Booleans, and also constructs as well. So things like if, then, and other things like that. Encoding all these different values as just as lambda abstractions. So for example, church numerals are an encoding of numbers. Church Booleans are an encoding of things like true and false as functions. And we can also encode more complex data types like lists and pairs and things like that as functions as well. And we're going to show you precisely how to do that throughout this lecture. So the question is basically, if I let you just use the Lambda calculus, could you still write sort of normal looking programs? And very surprisingly, the answer is yes, because you would think, well, surely I need some primitives and built-ins, things like plus and numbers. Surely I need some of those to actually do sort of real kinds of programming. But it turns out that you really don't. And this was probably the most profound thing to me in all of computer science when I learned it, and really one of the main things that sort of made me want to study programming languages. So this is basically the language that we're going to have you implement in assignment A4. So we're going to start with this thing I'm calling core scheme. So we're going to have recursive functions. We'll talk a little bit about what those are later if you haven't seen the letrec form before. Then we have normal let binding. We have multi-argument lambdas, which you implemented in A3, and then also calling lambdas with multiple arguments. Variable references, we're going to have if, and then we're also going to have a few different primitive operators, along with just some built-in data types. And we're going to compile it down to just this tiny language, which you should hopefully recognize by now as the Lambda calculus. So how are we going to do that? So we're going to write a function called church encode that's going to take our scheme like IR, or this language back here, and turn it into just the Lambda calculus. All right? And you can run the Lambda calculus in a few different ways that we've talked about. So one way is that you could just execute the Lambda calculus in Racket, right? Any piece of code in the Lambda calculus, you could just throw at Racket and Racket would evaluate it. But there are a bunch of other ways to do it as well. You can use things like textual reduction semantics. So you can just perform beta reduction on a sheet of paper if that's all you had, you didn't have a computer. You can also do things like use one of the other interpreters we've written, like the interpreter you're writing for A3. Now similarly, if you started from just that scheme IR, these are all valid Racket programs. So you could just throw them at Racket, and without converting them to the Lambda calculus, you could interpret them, and you would just get the answer. Let's say the answer in this case was just 2. And interp up here just means throwing them at the Racket interpreter. Well, now similarly, you're going to translate this down to the Lambda calculus, and it's going to produce a Lambda calculus term that in this case is an encoding of the value 2. All right, we'll talk about precisely how this encoding works right now. But let's say it's something like lambda f, lambda x, and then f applied to x, which is the encoding of the number 2 in our style that we're going to use here. Well, it turns out that we're also going to have a function that's going to take things from the Lambda calculus. This thing in the bottom right is the church encoded version of the number 2. And we're going to have a little function that's going to convert that back into the Racket number 2. But they're really the same thing. They're representing the same thing conceptually. It's just if you choose to represent it as the number 2 in Racket, or if you choose to represent it as a bunch of lambdas, right? And If this is surprising to you, think about the fact that the Racket number 2 is actually implemented using a pretty complex set of machinery for representing arbitrarily large precision integers, rather than just something like fixed width precision integers that's going to be used in a language like C or something like that. So there are even a whole bunch of different ways to represent numbers. You could, for example, have something like IEEE floating point numbers versus just normal unsigned integers or something like that. So this is just another encoding, but it's an encoding that's going to use the Lambda calculus to accomplish its work. And we're going to see precisely how to do that. So this is what we're going to start with. This is core scheme. So the first thing to tackle, because what we're going to do is we're going to take a bunch of these different forms and we're going to figure out, well, how do we translate those forms down to just the Lambda calculus? So I need to start with this language right here, and I need to get rid of all the different forms that I'm not going to use until I get just down to the Lambda calculus. So the first one is let. And this is a pretty easy form to get rid of. We talked about this a few times in class, but I'm going to talk about it again right here. Let is just lambda. All right, so let's see precisely why that is. Let's do an example of this. Let's go over to Dr. Racket right here. And let's say that I've got something like let x be the value 20 inside the body plus x 3. And then I compile that and run it, and it turns into 23. Well, I can equivalently say that is the same thing as the formula is to take this body right here, then wrap it in a lambda, x right here, and then to pass this value right here, something like that. And then I get the same thing. All right. So we can try that with some other examples as well. Let's do something like let x be the value, let's say plus 21 times 2, 3. And then I'm going to pass all of that inside of the let block is going to be maybe apply lambda y to x. So this would get translated how? Well, let's go back and look at our formula right here. We take the e body and we stick it inside of the body of the lambda right here. And then we take the let and we translate it to the set of arguments. So let's do that right here. So we're going to pull this, and this is going to become the body of the lambda. And then we're going to call that lambda with this thing right here. All right, so we get the value we expect. What if we have some multiple argument? What if we have multi-let? So let's do things like let x be 20, let y be 30, and then x plus y. So how would this translate? Well, let's translate this to be lambda x, y, and then the body's going to go right here, plus x, y. And then what's our first argument we're going to be? Well, this first argument here is x, so that should be what gets put here. So that's going to be 20. And the second argument is y, so that's going to be 30. All right. So we're going to do that right here. We get 50. All right, let's do something a little bit trickier. So I want to point out an interesting observation. When we do something like x and say it's 20, and then we'll do y and say it's x, and then we say x right here. So this is not something we can do in Racket. It's going to say x is an unbound identifier right here, right? Well, it's for the same reason if you tried to translate this, x and y, and the body would just be x, copying over right here, you'd run into an obvious issue. So you could make this x be 20, but then if you tried to make this x right here, it wouldn't work because x wouldn't be in scope. So you'd run into kind of a similar problem. So to make this work in Racket, the thing that you'd really want is a let star. So how can we translate a let star? Well, this is what I would usually call sequenced let. And so we can translate that as sort of a curried version of this. We talked about currying a little bit early in the class, and there are some good reasons to use currying. One of them shows up here in sequential let. So let's do something like lambda x, lambda y, and then this body x right here. And this first x right here is going to get the value, this first x is going to get the value 20. And then in here, we're going to call this with the value y, which is just going to be x right there. Get all that back out, and we get 20, as expected. All right, so there's a version of let star that you can cook up too. All right, so that's basically that translation. So now we know how to translate let, and we can turn them into lambdas. They're the same exact thing. This is actually something, that's a pretty common idiom in scheme programming. So if we do something like lambda x, x plus 1, and then I immediately apply that to 20, and it would be kind of stupid to write this in normal code because you would surely always just want to write plus 21. All right, so this is actually a pretty common idiom called left, left, lambda. And the reason it's called left, left, lambda is because you're sort of seeing this applied immediately to this argument right here. This is a pretty common optimization pass that happens in most production scheme interpreters. So for example, the Shea scheme, compilers. So for example, Shea scheme, which is a production scheme compiler that's pretty fast, and also the basis for Racket right now, we'll optimize this and inline this code. So it basically corresponds to inlining. All right, so you can make that fast. Okay, so next for currying. We've talked about this a little bit. So let's say we have a multi-argument lambda. So as you remember, in the lambda calculus, we're not allowed to have multi-argument lambdas. So things like lambda x, y, z, let's do plus x, y. Well, this is not valid lambda calculus code. Now the reason it's not valid lambda calculus code is because the lambda calculus precludes us from having multiple argument lambdas. We are only allowed to have one argument in our lambda, right? We can remember that because we can just go look back. This is exactly what the lambda calculus looks like. This only allows us to have one argument in this lambda right here. So how do we get rid of multi-argument lambdas? Well, it's pretty easy to de-sugar multi-argument lambdas down to single-argument lambdas just by using currying. So we translate, for example, this lambda x, y, z to a lambda x, lambda y, lambda z. And then the trick is that when we actually apply that lambda x, y, z, when we see something called with 3 different arguments, we have to figure out how to actually perform that application. All right? So let's say we have a lambda x, y, z. We know we can translate this. Translating to lambda calculus can be lambda x, lambda y, lambda z plus x, y. And now we want to pass in x, y, z. So let's say we had something like this called with 2, 3, 4. So this corresponds to x, the 2. 3 corresponds to y. 4 corresponds to z. We'd have this would be 2. This would be 3. Because then if you think about, if we get rid of the lambda x, we're going to end up with the lambda y. So then we're going to want to pass in 3 right there. And then go down to 4. And let's see what we get. Okay, so we get 5 and 5 each time. Okay, so the crucial part is that just like when if we have a multi-argument lambda that we've translated down into its curried form, well, now when we actually call that, well, of course we can't call it because the lambda calculus only allows us to apply things with one argument. But that's pretty simple, because every time we see something that has multiple different arguments, we can just translate that into blowing it out to actually perform the curried version of the application. And I'd also like to say there is one little trick here. So if you have a single or a zero argument lambda, so if you have something like lambda 30, that's just going to produce a function that if we call it, will produce the value 30. So how do we translate this? Well, it's not too hard. We can just translate it as something like this. And then when we actually call it, we can just call it with some nothing value, some meaningless value like lambda x, something like that. All right, so that gets us the same thing. All right, and then equivalently, because we're not using this x right here, we could have written the underscore. I kind of like keeping this identity function like that. So because we're not using x within this body, we could have replaced it with an underscore. So the trick is that we translate zero argument lambdas to the lambda that just doesn't take anything as its argument. Or takes one thing as its argument, but then that one thing isn't used. So equivalently, you could just do something like that. All right. Now you might want to prefer this style in typical Racket programming because this is a little bit more emblematic of the fact that you're not actually going to use that value. And so stylistically, we prefer this form instead. All right. Okay, so we've actually gotten rid of a few different forms now. We've gotten rid of let. So for example, you'll see that we don't have let here. We have let rec. We have lambdas with single arguments. So we went down from multi-argument lambdas to single argument lambdas. Also, all of our calls only have a single argument to them as well. So we don't have to worry about single argument application. And we have variables and ifs. So we have a few more things to deal with. So we're going to figure out how to get rid of the next ones. Okay, so next is conditionals and Booleans. So this is where it really starts to get interesting and fun. So let's think about how could we potentially encode these conditional operators. To do that, we have to come up with some way to represent the values true and false just with lambdas. So if we're programming in the lambda calculus, we don't get to have any built-in constant values. We just don't get to have those. We have to write those things out as lambdas instead. All right, so this is a pretty tricky concept to wrap your mind around. In the lambda calculus, there are no constant values. The only values there are lambdas. All right, and that's the most crucial thing to get. You're literally not allowed to write the value true or false in the lambda calculus. It's just not a value in the lambda calculus. So instead, we need to think, how could we potentially encode these things? And the trick is to realize that if we apply true if we put true in the guard condition of an if, then it had better produce the true branch of the if. And if we put false in the guard position of the if, well, then we had better produce the value of the false branch. All right? So that gives us a little bit of a hint. We could think about maybe encoding the value of true and false like this. So let's say, I'm just going to take this and literally copy and paste it. I'm going to define the value true as lambda true, false, true. Now you'll notice that I'm doing something here. I'm writing a multi-argument lambda. Now this is not a lambda calculus term, but I'm going to do this for convenience. I'm going to assume that you can curry this yourself so that you're only ever applying one thing at a time. So notice what happens. if I do an if of some guard here, and then I say v true or v false, let's say that I make that guard true. Well, I want this to produce vt. By contrast, let's say I produce something that evaluates to false. I want this to produce vf. So let's say that I translated this if form. Let's say that instead of making this if form, I translated this to just the application of the function true. And then the value vt, vf. What would happen? So let's actually try it out. So let's try true, 0, 1. And remember, this is standing in for if true, 0, 1. All right, well, now this returns 0. And look at why. Because I've made this value true, it's going to take in a true value and a false value, and it's going to produce the value true. So whenever I see an if form, if I see something like if and then some guard, 0, 1, I could just translate that to an application by treating this function guard truly as a function, and then 0, and then 1. And then really, what I need to do, if I wanted to implement this as a single argument lambda, which is what you'll actually have to do for project A4, is I'd have to go one step further, and I have to really write this out as lambda t, lambda f, and then t. Apply that to 0, apply this to 1. So that's just the curried form of it. Turns out there's a little trick you can use to actually use the little compiler you're going to write to implement this. So let's say that I do this. I get the value 0, as expected. All right, pretty simple to implement false. I can get the value 1. All right. Now, this encoding has a little bit of an issue. So what's the issue going to be? Because this is actually not quite the right encoding, although it is the right idea. So the issue is basically something like this. Let's say that I take the omega combinator. What's the omega combinator? The omega combinator is the combinator that doesn't terminate. So it's x applied to x, and then we apply it to itself. X applied to x. This is probably the most primitive, is the most primitive way to write a loop in the Lambda calculus, a non-terminating loop. So if I run this forever, it's not going to terminate. But let's see what happens if I put if true 1, otherwise omega. This is going to evaluate immediately to 1. And the reason is that the if branch does not evaluate the false branch if the if branch is taken. Similarly, I could swap this, put this to 1 right here, and I ended up with 1 there. All right? But it doesn't work that way in our encoding. So if I do let's say 0, this would be the translation of if true, because remember, this is how we're going to encode true. 0, otherwise omega. Now let's just run this to convince ourselves, and it produces 0. So our translation had better produce the same thing. All right, so let's try it and see if it works. This is the translation of true, and then we said if was translated by taking the guard, putting it in the application position, and then treating an if really as an application of the guard to the true and false branch. But note that something is going to happen. because Racket is a call by value language, it's going to evaluate each of the arguments to this function before this function is called. All right, so it's going to evaluate both 0 and omega. So that's too bad. Let's see what happens. Okay, so 0 gets produced, but now nothing else does. So there's a pretty easy fix for this. The fix is basically this. We're going to wrap both the true branch and the false branch in a 0 argument lambda, or it could be a single argument lambda that you don't do anything with, but let's just make it a 0 argument lambda for now. And then, right here, both true and false are going to be functions of 0 arguments, so to actually get this value 0 out, we're going to actually have to call it. So if we do that, then we've effectively solved the problem. And if you see why, if you remember, call by value says that you basically reduce until you hit a lambda, call by value and call by named. You don't reduce under lambdas. And so by wrapping both of the sides of evaluation for the true and false branch, if you wrap both of those in a 0 argument lambda, and then use and invoke that 0 argument lambda, what you're doing is you're delaying the execution of this true branch, and you're delaying the execution of the false branch, and then you're forcing the execution of the true branch right here, assuming that the true branch was actually taken. All right, so you can think of wrapping things in lambdas as essentially delaying their evaluation. All right, so that's the trick. All right, so that doesn't terminate, but we can wrap both of them in a 0 argument lambda. Now they do terminate. All right, so then we have our right behavior. Okay, so now our language is actually getting smaller pretty quickly. So we've gotten through, now we have single argument lambdas. So let's look here. This is just the lambda calculus. We only have a few forms to get rid of. So we have to get rid of let_rec. We have to get rid of plus and times. And then we have to get rid of cons, car, and coulter. All right, and then everything else we've taken care of. All right, so now let's talk about how to do natural numbers. So the trick here is to turn all the different nouns into verbs, or in other words, turn all of the numbers into actions, things that they do. So we're going to focus on the behaviors that are implicit in the values. So let's think about what a number is. Well, some number starting from 0, and we're going to assume something like Presburg or piano arithmetic, where we're starting from 0 and we're not going to encode negative numbers. There are more complex encodings that you can use to do that. We're going to stick with the simple one today, which is just starting from 0, we can represent some natural number as some function f applied in times to some value f, or some value x. So for example, the number 0 is going to be lambda f, lambda x, x. It's going to apply the function f 0 times. The number 1 is going to take a function f, and then lambda x, and then it's going to apply f once. What about the number 2? Well, it's going to take lambda f, lambda x, and then it's going to apply f 2 times. Lambda 3 is going to do it 3 times. So you can see the number of f's we've got out here is going to translate to the number of times we're going to do to perform that application. All right. So this allows us to define the function plus pretty easily, because let's assume that we've got 2 natural numbers. So let's say that we've got something like the number, let's say we've got something like the number 1. Oops. Let's say I've got something like the number 1. And I've also got the number 2. Oops. Right here. And then I want to do plus 1, 2. Okay, well, I'm going to tell you that plus is going to lambda n, lambda m, lambda f, lambda x, and this looks a little bit tricky, but we're going to see what it's going to do in a second. All right. So we're going to take this little encoding right here, adjust it so the spacing matches up. Okay, so this is going to be our implementation of plus. Now we need to call it with two different values. So this is going to be our first value, 1. This is plus, that's 1. And now we're going to call this whole thing. That's going to get rid of the, got this right here. That's going to get rid of the lambda in. And this is a curried application, so now we're going to get rid of the lambda m. And we're going to make m be 2. All right. And let's see what that produces. Okay, so this is a pretty complicated looking application. But let's see how it actually ends up. It ends up being not so hard. We just perform the beta reduction ourselves. So the first thing we're going to do is we're going to get rid of this lambda in right here and apply that to 1. So then we're going to be stuck with this, and we're going to inline the value for n. And then the value for n that we're going to use is going to be right here. Okay. And we've got this whole thing, and it's going to be applied to the value 2. All right. So it's still pretty complicated looking, but let's take it and figure out what it's doing. So now we're going to perform this inner application. So now we're going to get rid of the m. This is the value 2 right here. All right, and where is m? It's right here. All right. So now we're a little bit closer. All right, and let's look at what's going to happen. So I'm going to assert to you that this is equal to lambda f, lambda x, and then the application of f 3 times. F, f, f of x. Because that's what plus 1 of 2 should be equal to. All right, so this is what we computed it was equal to. This is what we think it should be equal to, because this is 3. So are these two things equal to one another? Well, let's find out. So how can we get rid of the f right here? So we've got a lambda f. We can take in that f is applied to f. So we can take this whole thing, and we can replace, because we've got the f right here, and we're replacing in the body, we can take it and just basically get rid of these. All right. And then we've got all of that applied to this. So let's take this right here, and then we'll put that in for x. Oops, I'm going to be careful about how I do this, because I'm going to get it wrong if I'm not. So we want to get rid of this application. This is the value that's going in for x. All right. And then we've got an f right here, so we're going to apply this one as well. So we're going to take this whole thing and replace it by, because we're doing an application of that to just f. So since it's an application of f to lambda f, we can replace all of this by just the body right here. So let's take that body right here. copy and paste that there for a second. All right, and then we've got to reduce this one still. So we're going to replace this entire thing because we're just applying this to this. We can take this and replace it by the body now. And now we've reduced it by performing beta reduction, and it ends up being the same. All right, so it's pretty amazing. It looks scary at first, but actually it's just a whole bunch of pretty simple beta reductions. All right. So what's the intuition here? Well, the intuition here is that this is going to perform f n times. That's what n is going to do. And m is going to perform f m times. So if I take f performed m times, followed by f performed n times, then I basically get n plus m. All right? So this is one where you really probably are going to have to sit it down, and even after having watched me done it on the video, you're probably going to have to sit and do it on your own and kind of do it on a sheet of paper. So if you work through 1 plus 2, that's a pretty good example. You don't really want to do anything too much bigger than that. Maybe even try 1 plus 1 and see how that works. All right? Now what about times? Well, it's pretty similar, except we're going to do something a little bit different. We're going to do, now n is going to do whatever its argument does n times. Now if we do m of f, that's going to do f m times. And if we do that operation of doing f m times n times, then we're going to get n times m. If we work out the math for that one, we're going to see it's a pretty similar thing. I'm not going to do that one, but I'm going to maybe let you work out what 1 times 2 is, or maybe even 2 times 2. You try this one out, you'll see pretty obviously what happens. All right? Yeah, the intuition there is we're going to have translate, basically we're doing something, again, this is going to be, m is going to be doing f m times. That whole operation is going to get done n times, and then we're going to apply that whole thing to x, which is going to give us n times m. And of course we could have written this as n, m, and n here instead, because plus sort of works, times works like that, right? You can rearrange it. Okay? So now we're at this smaller language. We don't have the arithmetic operators. All we have is cons, car, and coulter. All right, so we got an even smaller language to work with. And this is actually not much harder. So the fundamental problem is that we want a case split. So the solution is that we're going to take 2 callbacks, just like we did with true and false. So we're going to treat the empty list as a function that basically works like this. So the empty list is going to be translated as, empty list is going to be something like a function that takes a callback for when the cons is true, or sorry, when the value is cons, and a value for when it's null. We're going to call when null on 0 arguments, because null is not really providing any arguments. Similarly, cons of AB is going to be translated as lambda. So let's say cons of 2, 3 is going to be translated as lambda when null, lambda when cons, lambda when null, and then is going to call when cons of A, B, or in this case, 2, 3. Now, 2 and 3 are not elements of the lambda calculus, but we can use the encoding we just came up with right here. So this is 2. And then pretty easy to write out 3. Just add another f right here. 1 more parentheses. Great. So now we've got the total translate, the final translation of cons to 3. All right. So now let's see how they're actually going to be used. So now let's think about how can we define null? Well, it's pretty easy to define null. What we want to do is we want to write a little function that's going to take a con cell, and a con cell is something that's going to be a curried function that takes two callbacks. First, a callback to execute when something is true. When it's a, even I am forgetting the encoding right now. When it's a cons, so the first argument is when it's a cons. The second is when it's null, or when it's an empty list. All right. We can write this a few different ways. We can write it as a curried version. We can write it as a multi-argument version. Here I wrote it as the curried version. So let's say I define null, It's this little procedure right here. Define church null is going to be a cons cell. And remember, because cons cell is going to have been translated to the Lambda calculus, cons cell is a function. It takes two callbacks. The first callback is going to be what's going to happen when it's a cons cell. Now null should return false when it's a cons cell. We're going to call it in a curried way. The next argument is going to be what happens when it's a null or not a cons cell. Well, in that case, null should return true. All right. Now let's say, what am I going to do? So I'm going to define church null like that. This is my cons cell right here. What's going to happen when I call church null on this cons cell right here? Church null, perfect. Well, now I get the value false because this is a cons cell that's going to call when cons. All right. What if I had put in the what if I had used this encoding right here for the empty list or null? Well, now it's going to return true. And that's because we're going to translate the empty list as a function that takes a callback for cons, a callback for null, and just invokes null with 0 arguments, because what other arguments could you invoke it with? Null doesn't have anything else to tell you. All right. So that's how you can define null. All right, so now we're at a much smaller version of the Lambda calculus. We're pretty close. All we have is letrec. All right, so that's the next big thing we have to tackle is recursion. So it is super not obvious to me that if you don't have loops or constructs like recursion built into your language, that you can have recursive functions. This was something that always baffled me and made me feel really leery about programming in the Lambda calculus, because I always felt like, well, loops are the heart of programming. So if we don't have loops or if we don't have recursion, how can we have a function that's or how can we have a program that does anything at all, right? But it should be pretty obvious that we at least have some kinds of loops in the Lambda calculus. And that's because the omega combinator exists, right? We know that there are basic functions or basic combinators that we can write in the Lambda calculus that will actually loop forever. And omega is one of the most simple examples of that. And so we've been using that as an example for a whole bunch of different pieces of lectures throughout the course. So there is a combinator called u, which is lambda x applied to x. Omega is the application of u to u. So let's switch back to talking about Racket. So I'm going to write out a few different basic functions right here. So these are the kinds of functions we'd be writing all throughout the first week or two of the course. So for example, the factorial function, the Fibonacci function, Now, we can write those functions using a more primitive form called letrec. Letrec says, let me have, or let me define a recursive variable named fac, which is going to be lambda x, and then inside of this body right here, or inside of this definition right here, I'm allowed to use fib. I changed the name, but I was using it incorrectly. All right. So let me define recursively the name fac in terms of itself. So in particular, I can use fac right here. So I'm saying this is a function, lambda x, that says if x is equal to 0, produce 1. Otherwise, x times fac x minus 1. And then I call all of that, and then inside of the body of letrec, I'm allowed to actually call the function that I define. All right, so this is similar to using define, except you can sort of think of define as implicitly creating one of these letrec things. So letrec is really the more primitive form. All right. Okay, so right here, I'm calling fac. If I just had let rather than letrec, let's see what would happen. Oops. I think I'm messing this up because I'm shadowing the name. Here we go. So that's the problem. So if I do let right here, I try to call fac, Racket says fac is unbound because we're not allowed to recursively use this identifier fac within the definition of itself. However, if I change this to letrec, now suddenly I'm allowed to use fac in its own definition. All right. So what's the trick? How could I do this if I didn't have letrec? Well, I'm going to tell you. The trick is basically to use this combinator u. So u is going to take some function f and is going to apply f to itself. And this is going to give us all the power we need to allow us to do this. So now what I'm going to do is I'm going to translate this translates into, and the critical part here is that first I'm going to, let's take this and just throw this other thing away. First, I'm going to translate this as a lambda f. So I'm going to say, first, assume that I had a function f that was going to be the recursive version of fac. Just assume such a thing existed. If I could define fac in terms of itself, then here, instead of using fac, I would use the function f. All right? Well, I can't really do that because I would need to be doing something like calling f right here. So unfortunately, I can't really do that right there. But what I can do is I can call and apply this whole thing. I can apply the u combinator to it. Now what this is going to do is it's going to pass this entire thing into this entire thing. So f is going to get bound to this whole lambda f right here. And what that means is that this f right here is going to be a function such that if I call it on itself, I can make another copy of the entire function, and I can go around the recursion again. So the basic trick is to take this, add a lambda f in front of it, translate this recursive call onto an f. Then I'm going to apply this entire thing to the u combinator. But then, this is not the function immediately. This is just a way to make another copy of the function. And so that's going to allow me to make another copy of the function. So inside this body right here, if I call f on itself, I can get another copy of the function f, right? So basically what it's doing is it's allowing me to unroll the function one piece at a time, almost like pulling back another, sort of making another copy of myself. And this initial call to u bootstraps that whole process. All right, so let's just throw this entire thing away. Let's throw that letrec away, because now I'm not allowed to have letrec in my language. I'm just going to do this. And if I do that, then I get the value 6. And I didn't use recursion anywhere except for the fact that the u combinator is implicitly giving me the recursion. And this is a really, really cool mind-bending topic, right? The most critical part to understand is how f is essentially getting bound to itself, right? See, because inside this body, what is f? Well, because of the u combinator, f is let's bring this comment back down. Right here, f is this entire thing. So within this body right here, f is bound to itself. And if I call f on itself again, I'll get a copy of myself back. And that's what's so incredible about the u combinator approach to recursion. All right, and you can do the same thing for fib. So let's try this down here. So first I can go letrec. I can say letrec fib be lambda x. Take this whole thing right here. And call fib on 10. Okay, so that's my typical letrec-based definition of fib. So now I want to use it without letrec, so I'm going to translate it to let u fib be u of lambda f, and then this entire thing right here, lambda f, lambda x, except I have to remember, translate this, f, but it's not f directly. I have to call it itself here. And now I can call fib of 10. Oops, need to define u. So u is just this helpful combinator that we figured out to allow us to do this. All right, now we have our answer. All right, and now the y combinator. I'm not going to spend a ton of time on this, but let's just say that you don't want to have to, let's say you don't want to have to call yourself right here. Let's say you just wanted to be able to do something like f right here instead. Well, y is this special combinator that allows you to do that instead. All right, so there's a special version of the y combinator. I'm going to leave in some of the slides the way to actually derive the y combinator, but I'm not going to go through it right in this explanation. It's just a little bit tedious, and it's just a variant on the u combinator. I personally find the u combinator version easier to understand, but let's just define y right here. This just allows us not to have to unroll f. And I don't really feel like making too big a deal out of it, because it really is pretty much as simple as that. So this version is going to use y instead. Let's see. so this is the example I used from the slides. So let's see if I can get it to work here. Maybe I just have the wrong definition in the slides. There we go. So you can also define y in terms of u. Let's see if that works. Ah, okay. So I just had the definition wrong, or at least I pulled out the wrong definition. But there's a definition that we're going to give you, and you can basically just use verbatim. So this is a version that you can use verbatim for project A4. All right. All right, and you can do this with any recursive function, but that's basically the upshot. All right, so now that we're at the Lambda calculus, let's just talk about how are we going to get away from it. So if I just give you a giant thing in the Lambda calculus, how are you going to translate it back? So let's say I give you something like lambda f, lambda x, f, 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 x. So this is the church numeral I'm going to call 3. But let's say that I try to take this and I just try to print it out in Racket. What's going to happen? Procedure. Well, that's not very useful. I would really like to see 3 because I want to make sure that I'm actually going to pass the tests and that my project is not terrible. So how do I translate that into it? Well, there's a pretty easy way to get this going. So what could I do? What function f could I put right here? What Racket function could I apply this to change this, to actually interpret this and get the value 3 out? So what is a function f that if it's applied in times to some starting value x would give me n? Well, I could use add 1. And then I could apply this other entire thing to 0 as my value for x. And that is 3. So if I want to write a function church to nat to translate a church numeral to a natural number, I can curry call it on add 1 and 0. It works similarly for lists. I'll let you go through the encoding of that. You're going to give it what to do with a cons and a car. And you're going to tell it to convert. You're basically going to write a little recursive function that's going to walk down all the links. And then in the last case, we're going to say, well, if it is true, then return just the Racket value true. Otherwise, return the Racket value false. And that's basically as simple as it is. All right, so this allows us to write quite complex Racket functions and translate them all the way down into the Lambda calculus. All right, so we end up with some fairly huge fairly huge Lambda calculus terms. So this is a ridiculously inefficient way to write this, but this entire term is written in the Lambda calculus. And then all I have to do is translate that down into and reinterpret it as Racket code, and I'll get the answer. All right, so it's pretty amazing. We started with something that was just Racket code right here, and we rewrote it to a version that all it has is terms from the Lambda calculus. All right, and that's what you'll be doing in assignment A4. All right, so this is a really fun project. I'm really looking forward to it. All right, thanks.